DC motor, and I'll give you an example of how it looks in a few more moments, is a very, very straightforward invention. The diagram that you have in your book is repeated up here, and it has only a few moving parts, and these are the major parts that we have to explain its function or outline the functions for. So let's start with the first ones. The first thing is we must somehow, to employ the motor effect, remember the motor effect is a force on a wire because that wire is in the presence of a magnetic field and it also contains a current, that we must have a magnetic field. So we have magnets. Okay? Now the magnets can be in two different shapes. So most magnets, when you see them, are just flat-ended. Majority of really well-designed DC motors have curvatures in there like that, and that is to make the magnetic field really aim itself at the coil. Curvature here causes a radial field. That's a very bad colour. So we get a radial field. Now what do I mean by a radial field? As it goes from north to south, say this is the north over here in that diagram and south over here, the shape of the magnetic field is in and out. So it squeezes it in the centre. Okay? And this is where our coil is, right in the centre there. Okay? So the coil is really in a tight magnetic field. The more magnetic field on the coil, the more torque on the coil. Okay? Because torque, as we know, is NBIA cos theta, and B, magnetic field, gives more turning effect, torque being turning effect. So that's the first major thing in our motor, structure, we say. Now, do the magnets move? No, they are stationary. So we're going to use a term for stationary things. Things that do not move are stationary and they are part of the stator. Stator coming from the Latin root to be stationary, to be stopped. Okay? Anything that is stationary in the motor becomes part of the stator. Okay. Next, we need a loop of wire. Now, here is our loop going around there, and we know that we need more than one loop. If we can wrap it around 3,000 or 4,000 or 5,000 times, doesn't mean 5,000 by the way, but if we go around, we get more N. More N, more torque. So we don't just have a single loop. Here is a single loop in a diagram so that it makes it easier to see. We then now need to get a current in here. So here is a battery. Here's our power source over here. And the hardest part is to get electricity into our coil. And the problem being in the past was no one could come up with a great way of getting the current into the coil without twisting the wires. Now I want you to imagine this is our positive over here. Current would come in here and go into the coil in that direction there. And it would start to turn. Okay? If that wire is connected to that wire there, and this wire comes back here to the battery there, after a few turns, this would twist and tangle. And as someone mentioned yesterday, it's like using a hair straightener. Okay? And your hair curler, that's right, hair curler. So I had no idea what one was. Yeah. So apparently you get curled hair if you twist it around and you get knotted and tangled. So we have to come up with a really nifty way for the electricity to get into this coil and not to twist the wires. But there's another problem. Okay, so let's just, I'll just keep those annotations. I'll just write it out. Okay. And the way that it gets into this coil, so that you can identify it on your diagram now, is this really very, very ingenious device. This ingenious device is made up of two pieces. There is this thing here, which is a piece of metal in the shape of a cylinder, cut into two halves and then separated. Okay? So this is a ring of metal. It's really a cylinder. So we call it a split ring. Okay, so it's split into two. So it's a cylinder, which is split into two. And the name of the whole device is called the commutator. C-O-M-M, mutator. Okay? They've used the same words like from communicate. So this is the way that the coil communicates with the outside electric battery or power source. Now, with this requires us to have, what will happen is that this split ring is attached to each end of the coil. So this one over here, that part of the split ring there is attached to this wire here. And on the other one, let's get another colour, this one over here, that one there, is attached to that wire there. Okay, using black and red. That will enable to turn. So this split ring here turns. Now the problem is, the diagram has it that they're two separated pieces. And if you can happen to separate a piece spin, well what we do is we put in the middle of it, right in the centre here, we fill it in with a piece of plastic or insulating material, stick it into there, in such a way that we can stick it together and it turns as one entire object. It's got to have a high melting point because the commutator gets very, very hot as well. And this separates the two sides. Okay? And in a few more moments you'll see the commutator that has been split. And this metal disc, this metal cylinder rotates, and it rotates under two things called the brushes. A brush is just simply a piece of metal that does exactly what it says. It brushes along the surface of the commutator. Okay? So the first function of the commutator, and it has two functions, not one. So be very careful when you're answering what is the function of the commutator. It has two functions. The first function is to act as a way, a means, for current to enter the coil. Okay? So the first of its functions is to act as a way for the current to get into this coil. Okay, we're going to pause there and we're actually going to look at a commutator.